All right, friends, Ben again. This is attempt number 2 on a video for the differential equations class. What we're going to take a look at is Fourier series. So Fourier series are a way to represent certain functions as sums of sines or cosines. A question that should come to mind is, why do we want to do this in terms of sines or cosines? And two answers, the first of which is certain of the physical representations we want to do this sort of thing for actually desire to have a periodic function. So consequently, sines and cosines seem like a good way to represent things. The other reason is for something that we refer to as orthogonality, okay? So let me see whether I can actually get the iPad to work for me instead of me working for it, as it seems like it is. Come on, yay, all right. It is gonna work this time. All right, so the Fourier series, and let me see if I can lighten this up a little bit there. Okay, so the concept of Fourier series is going to seem like something that's completely weird and abstract and such, but it's really an extension of something that you've hopefully seen before. And then I'm going to stall as I talk to you because apparently my pencil does not want to talk to my iPad. Okay, now they'll talk. All right, so in a physics sort of context, you have hopefully seen this idea of, in 3 dimensions, we have the vectors. I think in there they like to refer to them as the x vector, the y vector, and the z vector. But in the math classes, we refer to them as I vector, j vector, and k vector. So I'm going to confuse you one step further and refer to them as E1, E2, and E3. The reason that I do that is that it's a common reference to refer to them with an E sub k when you're doing something that is an R upper N and you're doing all kinds of abstract blah, blah, blah stuff. We won't have to worry about that so much, but what hopefully you have seen done is taking the dot product of 2 vectors. And so if you get a vector like x1, x2, x3, and maybe another vector y1, y2, y3, the dot product just means to take their corresponding entries, multiply them, add up the result. So for instance, when you take this x vector that's just kind of generic there and dot it with E1, it's going to take the x1 times 1, the x2 times 0, the x3 times 0. In other words, it will pick off the x1 value there, okay? Similarly, if you dot with E2 or E3, that's going to pick off those entries for it. If we were using a different basis, and this is something from linear algebra, but if we were using a different basis, it would be convenient to be able to just take a dot product with elements of that basis and immediately be able to say what is the projection onto that basis element of the particular thing that we're dealing with, okay? So a similar thing to this dot product that we do with functions is referred to as an inner product. So you have to specify a particular interval that you're going to work with. And then the inner product between 2 functions is the product of the 2 functions, and then you integrate it across the interval. Now, that may not seem like there's a big connection there, but the thing that you need to think about is up here, we took each entry for the vector and multiplied the corresponding entries, just like we will multiply the corresponding values of f of t and g of t for different t values. Then we added those up. We had a finite number of things to add, so that was feasible. Here, there's an infinite number of different t values that you might be concerned with. So when we talk about adding those up, we're adding an infinite number of things. We're going to be using our infinite addition tool, which is the summation, which is an integral. So that's the reason why this inner product works like a dot product. And so consequently, we are going to want to look at taking the inner product between two functions. In particular, if you take a sine function and a cosine function, that's, I know it's hard to read there, but that says sine of mt and cosine of nt, with those being different letters, okay? And the values of m and n might actually be the same, but here we're going to purposely think of them at least as being integers. So because the sine is an odd function and the cosine is an even function, when you multiply them together, the result is an odd function. If we are integrating across a symmetric interval, boom, 0 every time, okay? So that says that a sine and a cosine are orthogonal to each other, kind of like these vectors up here are orthogonal to each other because their dot products turn out to be 0. So then further here, if you have a sine and, well, if you have two sines and they have possibly different coefficients there for the t, sine of mt and sine of nt, I am sure your Calc 2 class did not talk about the product to sum to product formulas, but those turn out to be important here. And so if you look those up, you're able to convert sine of mt, sine of nt into the cosine of m minus t minus the cosine of m plus t, all right? Why do we want to do that? Well, if you can get a sine or cosine alone and you integrate it across the period, as long as the coefficient of the t in there is an integer, well, is a positive integer, then you're going to go ahead and out of this end up with a result of 0. So here, if the cosine of mt that you're going, m minus nt, if the m minus n, if the m and n are different, then you're going to have an integer difference and your integral of the cosine will turn out to be 0. The m plus n, because we're only talking about positive integers, okay, the cosine of m plus n is going to turn out to be a positive integer. You're integrating across a multiple of the period, so consequently you're going to get 0 out of this business here. So if the m is equal to the n, that's the only time you have something different happen. And in that case, this cosine of 0 is just 1. So you're going to have 1/2 the integral minus pi to pi of 1 dt, and that's going to get you 1/2 times 2 pi, which is just pi. So otherwise, if the m and n are not equal, then we're going to get 0, okay? So that tells you that every sine function and every different sine function are orthogonal to each other, but that the sine of like 12t is not orthogonal to the sine of 12t. So as long as the coefficient is the same, then they are going to not be perpendicular or not be orthogonal, because that'd be kind of weird to be perpendicular to itself, okay? Well, do the same work then with the cosines, and you get the same kind of result. Either you get pi or you get 0, okay? So it would be kind of nice for us to get a 1 out of that instead, and it would also be nice if we didn't have to limit ourselves to a multiple of pi. So we use just a little linear transformation here, and we write these things out. The a sub m is 1 over L times the integral minus L to L of f of t times the sine of m pi t over L. So that'll divide out the length of the interval and so forth. Then we have something we refer to as b sub naught. There's not an a sub naught, just a b sub naught. The b sub naught is going to be 1 over 2L integral minus L to L of just f of t dt. What you're really doing there is multiplying it by the cosine of 0. And so it's just f of t dt. Notice that this 1 over 2L that comes out front is slightly different. Okay. Then for the cosines, it's f of t times the cosine of m pi t over L dt. Okay. So your function that you start with, you can represent it as this infinite sum with a couple of provisos. One is if your f of t is not continuous, it's going to have places in it that are messed up because sine and cosine are both continuous functions. So in any case, though, it will make it be something that is continuous. And then the other thing is that the new function that you get out of this is going to repeat every 2L. Okay, so best thing to do on this is to see something where we're actually doing it. So the question here is to find the Fourier series for this function. F of t is minus t and t depending on where you got it at. Let me make a couple of quick points here. One is that your textbook will use less than or equal to's in these places, and I don't bother because having one point where the function's not defined is not going to mess up things for the integration. So I don't bother to write them. Additionally, when you're typing, it's much easier. So anyway, though, then the part that I did not actually think to write down here is going to have period of 2 pi. Okay. If you drew a quick sketch of the function that we've got here, and we cut it off at minus pi and pi, and then we can talk about 2 pi and 3 pi separately. So the graph of this, just a rough sketch here, is going to do like an absolute value function, right? Because the absolute value is the negative of t. The absolute value of t is the negative of t if t was a negative in order to make it positive. For the absolute value of t when t is positive, it's just t, right? But then the periodic thing that this does is that now you will get a repeat of that function going on and on forever. So we're going to look at how we represent that with this Fourier series, and bearing in mind again that we we want to represent things in terms of sine and cosine because certain applications are going to have us doing things with periodic functions. Okay. All right. So in doing this, I always start with the b sub 0. So it's 1 over the length of your interval. Interval goes minus pi to pi. That's a length of 2 pi. So that's why it's 1 over 2 pi. So we're going to integrate the f of t over that interval and then divide. So with regard to that, I leave this hanging out front, and then from from minus pi to 0, it's minus t. From 0 to pi, it's just t. So then I'm just integrating polynomials, so those end up being pretty easy to do. I get 1/2 pi squared for both of those integrals there. So if you do the arithmetic of it, you end up with pi over 2. Okay. Then on the next portion, we're going to do the a sub m's, and we can do them all at once, and it's super easy. Barely an inconvenience. Your f of t, if you look at that picture, is an even function. Sine is an odd function. We're doing it over symmetric interval. Bam, it's 0. No need to do anything more. Okay. So then we're going to do the b sub m's. But yeah, Actually, let me go ahead and make this little caution. If you're doing these and you look at the function that you've drawn and you say, oh, that's an even function, then you don't bother doing the b sub m's. I'm sorry, you don't bother doing the a sub m's because the odd portion of it is going to just vanish. If you look at it and you know you've got an odd function, don't bother to do the b's because those are going to vanish. Most of the time you'll have a function that's neither odd nor even. So, all right, so the definition for the b sub m's has this 1 over pi. We're integrating minus pi to pi. And we've got the cosine of mt being multiplied by the f of t. So break it up into the two integrals. And we'll be going minus pi to 0, and we'll be going 0 to pi. In one of them, we get a minus t. In the other one, we get a plus t. Okay? But they're going to be very similar integrations to do. So with doing this, oh yeah, this confused me because look, it's the same thing. I copied it from the other page so that we wouldn't get confused, and then I got confused. So if I take and if I think about taking and factoring this minus out and stuff, notice that I've got a minus of a minus there. Another way to simplify this is to note the symmetry and then just say we're going to have an integral from 0 to pi of this, and then we're just going to multiply by 2. Okay, so that makes it a little bit simpler. Now, naturally, everybody here can do that in their heads, right? What? You can't? Crazy. I totally did this in my head. I mean, I didn't at all cheat or, let me see if I can even find where I cheated at. Oh, that's not the one I cheated at. That's a later cheat. So let me grab, yeah, this one here. And let me stop share and reshare. Somebody told me one day that this does not always switch windows when you expect it to. All right, so I had to integrate this t cosine mt from 0 to pi, and I am not a masochist, so I just went over to Symbolab and I typed it in and said, boom, what do you get? And Symbolab gives me this here, all right? And, oh, wow, and it shows me the steps. That is so evil. All right, so this that we've got here, I need to go ahead and copy out. But I need to be smart about it because some of it is not going to be necessary, right? So stop share, reshare, mirror, there we go. Okay, so just copying across from my Symbolab, I got here m pi, sine of m pi, cosine of m pi, then minus 1, and then this 1 over m squared out front, okay? Now, here's the thing with this. We have integer values for m. Sine of m pi is going to be 0, so just drop it. Then cosine of m pi, that is going to be the same thing as minus 1 to the m power. So that's why we write that there like so. Now, if you take a look at that, anytime that we put minus 1 to an even power, we'll get positive 1, and then this will turn out to be 0. So the result of this is going to be 0 if m is even, but if it's odd, we'll end up getting a minus 1 minus another 1. So we'll have minus 2 over pi m squared. Okay. Now, that's kind of a messy way to write this. We don't want to have to say something about a piecewise defined function and all this stuff. So I'm going to go ahead and use a value of k here and set it up so that 2k minus 1 will turn out to be m. So For k equals 1, you'll get m equals 1. For k equals 2, you'll get m equals 3, so on and so forth. Okay. So then I'm going to represent my f of t with this pi over 2 we got from the first integration, and then this portion here. So this would be the Fourier series representation of our function. And then when you look at your homeworks, there will be questions that ask you, hey, why don't you go ahead and draw a picture of this? And you will probably say, no, I don't want to. That's not fun. So give me just a second here as I open my Fourier examples thing to share screen with you. All right, so y'all should be able to see this. It is that code stuff, the Python code. So we're going to plot something, so we're going to have to use matplotlib, and we are in particular going to use the pyplot. Okay, actually I'm looking back at this and I think maybe I never used anything from matplotlib except for pyplot. Oh well. All right, so we'll start out with our data for plotting, and we're going to make this go from minus pi to pi. Notice that numpy has pi specially defined inside of it, and if you don't say np.pi, it may not understand. Probably a more efficient way to have done this would have been to say from numpy import pi, and then I could just type pi, but didn't think of it. Oh well. So I'm going to do this for 2 terms. Okay, I'm just going to go k equals 1, k equals 2. That's all I'm going to do. So, although I noticed that whatever. All right, and then I went ahead and did something kind of tricky and weird looking here. All right, so I took the pi over 2, and then I had to multiply it by np.1s of the length of t. So the t that we saw created up here on this line is actually a bunch of numbers going from minus pi to pi, and it just keeps all of them, track of all of them, and they are spaced out in units of 0.01. So I guess that's like 628 of them or something, but I don't want to guess. So instead of guessing, I'm just going to say, hey, make this thing here have the same number of things in it as t did. And that's just for bookkeeping so that you can add all these things together efficiently and stuff. So in any case, though, the np.1s basically just takes the number 1 and repeats it a bunch of times. And so when we're multiplying it by an actual number here, then it'll be more convenient to add it to t and stuff. All right. This next bit here is a for loop. So I'm going to say for k in np a range of n. So that's going to go 0, 1, 2, 3 up to n, right? And bear in mind, I said that wrong. It goes 0, 1, 2, 3 on up to n minus 1. It never does n. Seems super inconvenient, but it's what programmers do, okay? So to fix that, my m I'm going to talk about, I'm going to have 2k plus 1 instead of 2k minus 1. So it's just a quick fix there. And then because all of the things, all of the coefficients that I had, my, what was it? A sub ims or B sub ims? All my B sub ims were actually negative. I'm going to, on this line here, tell it, take S, which we already defined with that constant there, and subtract from it, take the same thing and then subtract from it 2 times NP's version of cosine MT, but you have to divide it by pi times m squared, okay? And then all the rest of this is just code to make the plots go right. Oh, and I forgot that I had this in here. I don't really need to save the figure every time, so I'm going to comment that out. All right. And then I'm going to hit Command Enter, and it's going to evaluate it. And you look at the plot there and you say, yeah, okay, that kind of looks like an absolute value. But maybe we go back up here and say, let's do 20 of them. And now that really looks pretty good, right? If you zoom in a lot, you can see that it's rounded at the tip. But that's a pretty good picture there. And then if we step back here and say, oh, let's go out to 5 pi, and tell it to draw it again, you can see it draws this portion, we had before, and then a few more copies of it. All right. So that is plotting that. Okay. So I do ask you in the homework to do some plotting, and I don't tell you exactly how many terms to go out to. I want you to experiment around with that and see what happens. So, all right, then let's do one more example. That one was an even function, so let's look at an odd function. Because of time constraints, I'm going to not do one that's neither even nor odd. So, sorry if that disappoints you. Come on, dude. No. I have to pause the recording and reboot my iPad. Hello, friends. I'm back. Let's find out whether I can share the screen now. Yay, I can. Okay, this is very annoying. I am consequently going to go through everything here, even though what I need to be doing is to break and jump across to things, because I just cannot reboot my iPad every 5 minutes. It's just ridiculous. All right, so the problem, and I can't connect my damn pencil every time. So what we've got here is looking at finding the Fourier series for a function sketched below. So from the sketch, you could see that this function, wow, okay. You can see that this function is an odd function. That is to say, this part here is reflected over here in rotational symmetry. And if we continued on, we know that we would want to continue the function going on. So I do want to tell you, though, you might get one of these where it says, take g of t equals 1 minus t. So that would be here on 0, 2, and just do it like that. And looking at it, you'd go, crack, that's not a symmetric interval. You know, it doesn't have any of my nice symmetry sort of things going on. What will I do? And the thing that you'll have to do is to, let's see if I can make this look right, is you would get something like that, and then you would notice the symmetry to it, and you would just make the copy and get the symmetric interval, okay? Now, you could do this from -1 to 1, or you could have done this, I suppose, from -2 to 2. Either way, you should get the same result. Just there'll be different steps along the way to get there. Not much different, same ideas, all right? But I set mine up, oh no, I set mine up on the symmetric interval there. And I went ahead and said the or equal to's on it, which I just got through saying to y'all that I don't do. So I'm going to just take those back off and let it have those jumps, okay? Do notice that this is different than the previous example because here we're going to have jump discontinuities happening at all of the even integers. So, and that is gonna have something nice. So anyway, though, once we've noticed that we're dealing with something which is which has this odd symmetry to it, then we're going to go ahead and calculate the a sub m's, and we're not going to bother with the b sub m's because we know those will turn out to be 0. So we are integrating here from -1 to 1, and that means that the L that we talk about is going to be 1, and then the 1 over 2L will be just 1/2, and your G of t and your sine. So kind of like the previous example there, we had to break it up into the -1 to 0 and 0 to 1. And from -1 to 0, you get minus t minus 1. But from 0 to 1, you get 1 minus t. Okay? But the integrals will be pretty much the same kind of thing. So then I go ahead and this is just a copy of the same thing here. And I looked at it and I said, oh, you know what? If I break this apart and take the -1 times the sine, and then the +1 times that sine, and then the minus t times that sine, and then the minus t times that sine, maybe that's going to make things a little bit nicer. And the thing that I observed from that is that this and that are actually going to give me the same thing. In fact, here on this part, since I'm integrating the same thing across these two adjacent intervals, I could have just joined them together and said it was -1 to 1, but going across the interval -1 to 1, t times sine t, both of those are odd, so when you multiply them, you get an even function. So consequently, I do get to do that trick about 2 times the integral across half of it. 2 times the integral across half the interval. All right. So then I just have to integrate these two things. Oh, but wait, the 1/2, I can distribute that through, right? And then I just have to do these two integrals. And again, I turn to Symbolab to do them and copied them down here onto that. And I notice that sine mt, that's going to be 0, so I can toss that out. And then the cosine m pi will be -1 to the m. And so I just have to subtract them. And of course, one of the m pi's will cancel out, and then I can put those together onto a single spot on that. Okay. So keep in mind that I paused meaningfully here. Okay. Because then when I come up here and I want to have my f of t turn out to be that, then I went and plotted things using Colab. But when I plotted things, I turned out to get a picture that told me I was wrong. Now, you have to understand with regard to this, mathematicians, by and large, we are super arrogant, and we never, just say, oh, we're wrong. But when you're wrong, you're wrong. And so you have to figure out what's going on. So the thing that I did was to go back to Symbolab and asked it to do the integration in a slightly different way. And then the result I got was 2 over m pi for some reason. And I was like, what? What the heck? And the thing that's going on with that is back here, this minus sign I didn't copy it. Man. So that means that when we are doing this bit here, that we are actually adding and subtracting a -1 to the m, which means that we will actually, yeah, sorry, didn't write that right. The adding and subtracting, yeah. I'm sorry. I'm going to leave that with the 2 hanging in there. Anyway, they should just cancel out. And I still have some sort of an algebra error here that I can't quite figure out. Because this should get me 2 over m pi. And I'm not entirely sure why it's not working. So if you have some insight, please help me out on that. Okay. So I'm going to stop share on that, but bear in mind that we're going to look back at that formula. And and I have to switch tabs beforehand. And I'm going to go ahead and show you all. Gosh, this is such a pain. Yeah, I'm going to show you all the Symbolab integration first. And that gives, advertisements for UNCG. Didn't know that you were going to get advertisements in the middle of class, did you? And all right, so the thing that I did with the integration here was I just said integral -1 to 1 and integral 0 to 1 and stuff like that. Oh, I just noticed something. I just noticed a minor error here. We'll fix as we go. Notice I did not have the 1/2 sitting out in front of that. So I'll need to take care of that. But I told us to do the integration. It goes ahead and showed the steps. I don't really care about the steps right now. And we end up for our answer getting 2 pi m minus 2 times the sine of pi m. Again, sine of pi m is going to turn out to be 0. So we have 2 pi m over pi squared m squared. So that means we have 2 over m times pi. Okay. And so then I will stop share on that and jump across here to my Fourier examples and do a share on that so that we can see how that came about. All right, so we had our first plot there. All right, so then I was doing this second plot here. And again, I had this all cleverly planned out to have y'all see, oh no, Ben made a mistake, and see how we fixed it. But things are not cooperating. So I went along here with the same setup, but because of the fact that my b sub 0 would turn out to be 0, instead of np dot ones, I'm going to go ahead and use np dot zeros. So it'll generate a bunch of zeros in there. There's another thing called zeros like, but I haven't experimented to make sure that that does what I'm trying to do here. So anyway, I start with my S being zeros, and then I'm going to go ahead and have my M go from 1 to the n plus 1, okay? And then I'm going to have it do the sine of m times pi times t. So the first time I graphed this, I made another mistake and didn't put the pi in there. So, but then times that weird formula that I had before that turned out to not be right, okay? So I hit Command Enter in order to evaluate it. And then I can see my function is an odd function, but it doesn't have the shape I wanted. I wanted it to have slopes, a slope of -1 here between 0 and 1, and yeah, and the same slope over here. So, clearly something went awry, and I have to figure out what went wrong. Like I said, I went through and got my correct got my correction there using Symbolab to do my integration, and then I think maybe I'm supposed to have a 1 here instead of a 2. Let's check to make sure. Nope, not looking like it. Okay. Yeah. So for just a relatively small number of n values, you notice it starts to get the shape, but it's all wiggly and stuff, right? And so if I go back up here and tell it to do that for 50 of them, it's going to look much more like the shape that I wanted to get out of this, right? Now, the only thing is, if you can zoom in further, you'll notice that it's all wiggly all along here, but the wiggly keeps flattening out, except for right here. Those those places right at the ends where it's fixing to jump, fixing to, I sounded really southern there. Those places where you've got a jump discontinuity around them, you will always have that kind of an extra wiggly stuff. It is referred to as the Gibbs phenomenon, and it just says that at points where things are discontinuous, that these Fourier series aren't really super good. And so if you're able to take the infinite sum, it always gets good, but you can't take the infinite sum. You have to be settled with, you have to be happy with like 500 terms or something. So anyway, though, that's a couple of examples of working out Fourier series. And so I'm going to ask y'all to do some of those in the homework. It's not super hard, but let me tell you, having Symbolab or Integral Evaluator or Wolfram Alpha do your integration for you, that's nice. So, all right, I'll let you go. See you in class.